Good morning, everybody. We are starting. So first, short announcement. There's going to be a quiz, not this week, not next week, so 2 weeks from now, a week before Hanukkah. I think it's scheduled on Wednesday morning, but an official announcement will be sent to you, hopefully today or tomorrow. Also, this announcement will include what is the material for the quiz. I remind you that the quiz is 22% of the final grade. Great. So, where are we located in our material? So we are dealing with micro, or before that, we had the following expression, which is sum over I, E of I, E of I. This is the expectation, right? The expectation of the energy for the system, or in general for any observable. For any observable O, the average value is sum over all the possible states. The probability of the system to occupy the state multiplied by the value of the observable in the state. So O is observable. What we are trying to do is to make specific assumptions about the probabilities and the energies using specific models. Let's call them ensembles, which are assumptions regarding P of EI and EI itself. Each ensemble that we will use, and we will use 3 different ensembles in this class, there are specific assumptions about the probabilities of being in a specific state and the different values of the state. We started to treat the microcanonical ensemble. Microcanonical ensemble. Where are 3 different assumptions. So probabilities are homogeneous. Homogeneous. Okay. Energies are the same for all states. Okay. 3, we use this definition of the entropy S equals to K Boltzmann log of omega. Omega is the number of states. Number of states.
What is the second?
Sorry? Energies are the same for all states. Same. So those are our assumptions, and the path to calculate anything, okay, is based on the third guy over here. We'll see that this entropy is actually have a more general definition, and this specific form is applicable only to the microcanonical ensemble. It's slightly different for different ensembles. But the path to calculating anything, okay, it is calculating 3, calculate S, okay, or let's call it the algorithm. The algorithm for solving problems in the microeconomical ensemble. One, calculate omega. Two, calculate S equals K Boltzmann log of omega. Three, use 1 over T equals to ds to dE. The number of states is actually dependent on your energy. So let's say 0, set E. Use the 1T ds dE to obtain thermodynamical relation. Right? It's actually very, very simple. The only problem is this. Everything else is very, very, very technical and very, very, very simple. Some simple algebraic steps. The only problem is calculating the number of states that you have in the system. As in all the problems in statistical mechanics, you have to have a model in order to see what's happening. So you need to use examples. So this is what we're going to do. We're going to use specific examples to observe the behavior based on the assumptions of the microcanonical ensemble and the algorithm for solving any problem that you might encounter when you're dealing with microcanonical ensemble. So two-state model. Two-state model. That's what we are going to solve. Hopefully we will manage to solve it to the end of the class. What is a two-state model? So first of all, we start with a gas of particles. Why we start with the gas of particles? Well, because usually we can solve, and I will explain later why, systems where the interactions are not too strong. Okay? So we're starting with a system where the particles, they do not interact with each other. Okay? And there is total and particles in the system. Now, the energy of each particle, so the particles are not interacting. It's very important. The moment that they start to interact, we are doomed. But unless they're interacting, we can solve almost everything. Now, if they're not interacting, I need somehow to define the energy of each particle. So what I'm saying is that for each particle, every single particle, two states exist. Okay. So this is the energetic spectrum of the particle. Energy of a single particle. And the energy in this minimal model is either 0 or epsilon. Okay, that's it. Very simple two-state particle. There are many examples in physics that you can look on different systems and you can basically say, well, I actually have only two states in this system. Okay. We need this discretization because it makes the life simpler, and it's not something which is completely made up, because you have a bunch of systems where you have this separation, and actually it was extremely applicable to the physics of semiconductors. because you have conducting bands and there are separations between the band, and you can say that each band is a specific state of the particle. Great. So I want to understand something about this system, how it behaves as a function of temperature. What happens if I heat up this system? Specifically, a very applicable or experimentally measured quantity is the heat capacity. So we want to look on dE dt, because this is something that can be measured, right, and explained and observed. So we want to calculate the heat capacity for this system. On the way, we want to obtain what is the energy of the system, etc., 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 as the function of the temperature. Okay, so we have our algorithm, and we work according to this algorithm. As I told you, everything becomes simple when you understand what you're doing. And here, everything is set of computing the number of states in the system. This is what you do in microcanonical interval. So stage number 0, we set energy. So energy is E. So this is the energy of the system. Okay. Next, we need to compute the number of states for the system as the function of the energy. How do I compute the number of states? So what do I know? I know that some of the particles are sitting in the ground state, their energetic ground state, and they have zero energy. Some of the particles sit in the excited state at the epsilon. So the number of states, if you think about it, the number of states is basically how many particles are in the excited states, how many particles are in the ground state, and how I can move them around. So for example, let's assume that I have a blue particle, a red particle, and a green particle, or black particle. Okay. And I tell you the following thing. This is setting the energy. I'm saying that the total energy of this system is epsilon. The energy is set to epsilon. Okay. This is a specific system with n equals 3. I set the energy to epsilon, and now I want to compute what is the number of particles in my system. So I'm looking on the different representations of the energetic spectrum. I can have the following state. Now, when I mean state, it's not the state of a single particle. This is the state of the whole system, right? So I can look on the system and can say, well, in the epsilon, or in the ground state, I have two particles. The red particle and the black particle. And the excited state, I have only one particle, which is the blue particle. This is one specific state of the system. What is the energy of the system in this state? Epsilon, right? You count, because they are not interacting. The total energy is the energy, the sum of the energies of the different particles. 0 plus epsilon. The total energy is epsilon. Great. This sets the constraint that the total energy is epsilon. I'm looking on another situation. Here I would have blue particle at the ground state, red particle at the ground state, and black particle in the excited state. Okay. This is actually satisfies the constraint that the total energy is epsilon. Great, yes. So this is another state of the system. I'm going again, and now I'm looking at the excited state. I finally put the red particle in the excited state, blue particle at the ground state, and the black particle is also on the ground state. This state satisfies the total constraint that the energy of the system is epsilon. Great. This is also a state of the system. Do I have any additional states? I have three particles. The constraint is that the total energy is set to epsilon. Can I have a different configurations of those three particles such that the total energy is going to be epsilon? What do you think? No. There are no other configurations. I counted all of them. So for this system, omega of epsilon is equals 3. Right. So what I understand from this specific realization, when the total energy is epsilon, the number of particles is 3, that in order to obtain the number of states, I need to calculate the total number of configurations possible to the system under the constraint. What is my constraint? I set the energy to be E. This is a specific constraint. Okay? Not any configuration is possible. Right? So it's a combinatorial problem. Right? Some of the particles I'm going to put in the excited state. Some of the particles I'm going to put in the ground state. How many configurations I'm going to have? Okay. If we look for general N and E, not a very specific epsilon and 3, how many particles are in the excited state? In the excited state.
Divided by E.
E over epsilon?
Mm-hmm.
No.
And choose E over epsilon.
Wait, no. Or maybe yes? What do you think? And not by choosing. I'm saying if I add up, I'm looking on all the different systems, all the particles, and I'm saying all the excited particles have energy epsilon. And they sum up to E. So you were right. It's E divided by epsilon. Right? So I have E divided by epsilon in the excited state. The number of configurations, like I plotted for you over here, is going to what? I have total N particles. I'm going to choose out of those particles E divided by epsilon particles that are going to be in the excited states. I don't care about the order, how do I choose them, right? And the moment that I chose a single particle, I'm not getting it and I'm not delivering it back to the pool. So it's a combinatorial problem of choosing E divided by epsilon out of N, right? So whatever you said choose, what is this? It is N over E divided by epsilon. Okay. So this is N factorial divided by E divided by epsilon factorial and N minus E divided by epsilon factorial. This is the total number. Right? I took a physical problem and I translated it into a combinatorial problem of choosing such and such number of particles of such and such total number of particles, and this is the answer. Okay, so I did, was 0. I set it and it's okay. The next one was to compute the number of states, and I also succeeded in it. This is number 2. Or number 1. What was number to computation. The entropy, great. So 2 was the entropy equals to K Boltzmann log of omega of E. All right, so here we have to play a little bit, okay? In a little game called algebra. Because eventually you want to take a derivative out of it with respect to the energy, etc., etc. So you need to massage this expression a little bit. It's not enough just to plug this guy inside and say, oh, S equals to K Boltzmann log of n factorial divided by E by epsilon factorial and n mean minus E divided by epsilon factorial. It's not enough because in number 3 you have to take a derivative and you have this ugly factorials inside and you want to do something about them. Great, we're going to use the Stirling approximation. So we're going to massage this a little bit and we're going to use Stirling approximation. So some algebra. Something like 3-4 minutes. Not too much. Okay. So what we do with the algebra, we start first to apply the logarithm rule. So S equals to K Boltzmann. What we have inside? We have a logarithm of n factorial. We have minus a logarithm of E divided by epsilon factorial. And we have minus logarithm of n minus E divided by epsilon factorial. This is what we have, right? Now, as you said, we need to use some sort of approximation. So first of all, so what do we do? Remember the following thing. What is n factorial? Do you remember? It is square root of 2 pi n divided by epsilon to the power of n. Multiplied by n over. So this is the Stirling approximation. Stirling approximation. Where you usually have been told it in a slightly different way. You forgot about the prefactor over here, right? And the Stirling approximation, how it's usually described to you, is that log of n factorial, I don't know exactly what this means, but approximately, it is n log of n minus n, right? This is what you've been told. You're also being told another story. When this approximation works, big N, right? How big?
Very big.
Very big. What is very big?
As much as we want to.
3 is big?
Depends on...
3 is big. This approximation, despite whatever you've been told about the large number, works from 2.5 already very good, exceptionally good. And can be 3. And you won't notice a big difference between the n factorial and this guy. N does not have to be big. Okay? This is a lie. Okay, so we're using it. In our case, we can use n is big, but it doesn't really matter because 3 is actually good enough. 10, 100 is wow. You need a microscope in order to see anything. Okay, so we're using this approximation. We are forgetting about the square root of 2 pi n because it will, get out. And we start to look what we have in all those parentheses. So it equals to, we have K Boltzmann outside of the parentheses. Here we have n log n minus n. This is this part. This part goes as minus what we have inside, E divided by epsilon log of E divided by epsilon, and minus E divided by epsilon. So this is this is this, and the final guy is minus, inside of parentheses we have n minus E divided by epsilon log of n divided minus E divided by epsilon, minus n divided by n, not divided, n minus e divided by epsilon, and we have a lot of parentheses over here, but we are done.
Why do you need the Stirling
Why do you need a Stirling approximation? Because eventually I want to take a derivative of this with respect of this, with respect to epsilon, and what is the derivative of e divided by epsilon with respect to e?
Technically, you can use the fact that like factorial is like multiplication, and you can like switch.
So you have a e by epsilon multiplications of a lot of stuff, and you have to take a derivative of a multiplication of e by divided by epsilon.
But you can
things.
use the logarithmic characteristic of you can use switch it and make it a sum of bunch of logs.
This is what I'm doing.
No, but inside the factorial you switched it into bunch of smaller ones.
What is the nicest expression when I take a logarithmic of this guy, okay? The nicest expression then that afterwards I can actually take a derivative. The answer is Stirling. In Stirling, you have two terms, and that's it. Now, if you do whatever you're suggesting that we will do, I will have n minus e divided by epsilon terms that I will have to take a derivative of each and every one of them to n minus e divided by epsilon. Unlike n, this can be extremely large. Okay? Their answer is yes, I can make make the multiplications of the factorial explicit and take the derivative term by term, where I'm going to have a sum, or I'm going to replace this log by two terms, which is also a sum, but very small one. Okay? Other questions? Yes.
Can't we replace the factorial with a gamma function and then...
It's exactly the same thing. Exactly the same thing. Gamma function and n factorial, it's exactly the same thing, like just gamma function is defined on non-integer n's. That's it.
Yeah, but then like we get...
You're going to use Stirling approximation. It doesn't matter. You cannot escape the Stirling approximation. This is the simplest thing that you can do. Anything else, any other transformations, it's going to make your life extremely harder. Don't do it. Okay? Okay. Now, we have to play with it a little bit. We can take the derivative out of it, but it's usually preferable to play with things before you do something. Okay, so first of all, let's delete stuff that we don't need. What do we don't need? We have minus n here, and we have minus n. So this guy goes away, this guy goes away. We have minus epsilon divided by e divided by epsilon, so this is e divided by epsilon, and we have minus e divided by epsilon. This guy also goes away, okay? And we're left with K Boltzmann and log of n minus e divided by epsilon log of e divided by epsilon minus n minus e divided by epsilon log of n minus e divided by epsilon. Okay. Well, basically I can take the derivative already now, but I want to describe to you that it's we can make all of this even nicer. So what we are going to do, we are going to take all the n's together, okay? N's not inside the logarithm and outside of the logarithm. So we have K Boltzmann, we have n, and here we're going to have, so I'm taking this n together with this guy. Okay, so we have n logarithm of what? Of, let's write it down, of n divided by n minus e divided by epsilon. Okay, so this is those two terms. In addition, I'm going to take the e epsilon and this term over here. So this is minus E divided by epsilon log, and we have here minus minus plus, so it's minus, so it is E divided by epsilon divided by n minus E divided by epsilon. Okay. Great. So what else can we do? So first of all, I would like to take n outside of the parentheses. Okay. Now, why should I do that? I'll explain to you in a second. So we have n k Boltzmann. Here we have, so let's cancel all the n's. N. So we have a logarithm of 1 divided by 1 minus E divided by n epsilon. Okay. And we have minus E divided by n epsilon, a logarithm of what? Of E divided by n epsilon divided by 1 minus E divided by n epsilon. First of all, why I have done that? I'm looking on this, saying, well, this is my S. Looking on this, well, I actually did something okay. All my approximations so far are good enough. At least in this specific perspective that I'm focusing on. What is the crucial property of the entropy? It has to be extensive. Entropy has to be extensive. Now, if I'm in making my system larger, okay, n goes to 2, the energy goes to 2, so everything cancels out. Due to this presence of n outside and the fraction of E divided by n, I know that all of this function is an extensive function. Okay? When I increase the energy by 2 and I increase the size of the system by 2, everything cancels out. And the only thing that I will have a prefactor of 2 over here. Great, so this function is extensive. This is actually, this is good enough, but I can make it better. You know what, I can make it better.
Stas, how did we get that last passage?
Where from?
From the last one there to the first one.
I cancels the n. N, and then n has to come over here. Okay, the same happens over here. Okay, okay, so I can write it down as n k Boltzmann of one minus E divided by n epsilon multiplied by a logarithm of 1 over 1 E divided by n epsilon, and I have a minus E divided by n epsilon, a logarithm of E divided by n epsilon. Right? You see what I've done? I've collected this term with this term. Okay. Can rewrite it again as n k Boltzmann, and here I have E divided by n epsilon minus, I'm sorry, I wanted to write it the other way around, minus 1 minus E divided by n epsilon, a log of 1 minus E divided by n epsilon, and I have a minus e divided by n epsilon of log of e divided by n epsilon. So this is my entropy. So why exactly I want to do this, some games, and not saying, well, Stas, you got this long expression over here, it's fine enough, let's take a derivative. Because it's actually much more easier to take a derivative of this pattern, right? So when I'm looking on this, saying, oh, it looks like x log x, right? So I have, right? So if I say, oh, this is x, this is log of x, this is x, this is log of x, right? Because the next step is I have to take the derivative of ds to de. Okay. Now, I have to take the derivative of two terms. One, d to de of this guy, 1 minus e divided by n epsilon of log of 1 minus e divided by n epsilon, and d to de of e divided by n epsilon log of e divided by n epsilon. Those are the two derivatives that I have to take. Now I remember this very nice formula. D to dx of x log x equals to, what it is equals to? Do you remember? Log of x plus 1, right? This is what I have, log of x plus 1. So here I can use exactly this form. Every time that you look on some different formulas that you have on board, try to find patterns. It's much more easier to work with patterns. Okay, so I'm taking this derivative over here. It always, you can always, take the hardest path, just to do it bluntly and that's it. But if you work with patterns, it's much more easier. Okay, so from this guy, what do we obtain? According to this formula, it is log of 1 minus e divided by n epsilon plus 1. But we are not taking a derivative with respect to 1 minus e divided by n epsilon. We're taking the derivative with respect to e. So we have to multiply all of this by an inner derivative. What is the inner derivative?
Minus 1 over n epsilon.
Minus 1 over n epsilon. Out of here, what we get? We get log of e divided by n epsilon, right? And here what we have, plus 1, and multiplied by the inner derivative. What is the inner derivative? 1 over n epsilon. Okay. So in total, 1 over t equals to ds to de equals 2. Now what we do, we know what is the derivative of this guy, we know what is the derivative of that guy. Okay, we have to multiply everything by nk Boltzmann. So we have nk Boltzmann, what we have inside. So we have minus, right? Minus of log of 1 minus e divided by n epsilon plus 1 multiplied by minus 1 over n epsilon. Okay. So this came from this term. We have another minus. Okay. We have another minus. And in this another minus, we also have log of E divided by n epsilon plus 1 multiplied by what? By 1 over n epsilon. And that's it. Okay. What cancels out? Minus, plus, minus. Minus, plus. So this guy and that guy, I don't need. Okay? Okay? So I have that 1 over t equals to, what else cancels out? I have n over here and 1 over here. So 1 over t equals to k Boltzmann. I'm taking 1 over epsilon out. And here I have minus minus, so it's a log. And here I have minus. Okay? So I have a log of 1 minus e divided by n epsilon divided by e divided by n epsilon. Very nice expression. Okay. Very nice expression. So we're almost done. Don't worry about it. So what we have on the right hand side, we have epsilon divided by k Boltzmann t equals to log of 1 minus e divided by n epsilon divided by e by n epsilon. We take an exponent out of this. E to the power of this guy equals to e to the power of that guy. So we obtain e to the power epsilon divided by k Boltzmann t equals to 1 minus e divided by n epsilon divided by e divided by n epsilon. Let's solve this. So what we obtain, e divided by n epsilon multiplied by e to the power epsilon divided by k Boltzmann t equals to 1 minus e divided by n epsilon. Okay, so e divided by n epsilon. Here we have e to the power epsilon divided by k Boltzmann t minus 1 equals to 1. Sorry? Plus 1. Plus 1. And e divided by n epsilon equals to, or this, e equals to n epsilon e to the power minus epsilon divided by k Boltzmann 2 divided by 1 plus e to the minus epsilon by k Boltzmann t. This is our expression. That's it. That's the energy. Now, here, we turn the wheels a little bit around. So how we started? We started by saying, oh, we set the energy, and out of this energy we obtain some sort of connection to the temperature. Great, so we found this connection, we found this expression. Here I can play with the model a little bit, right? I can say, okay, so what I've done is I started with energy and obtained what temperature is. Let's turn the wheels around, all right? Let's turn the picture upside down. Saying, no, let's fix the temperature and we will obtain what's the energy of the system. So this is what it actually gets us to, right? So you do all these things, you said, oh, you set energy, it's a constraint, etc., 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 etc. You have a bunch of boards, but you work hard, and then you say, no, but actually I want to control temperature. Because this is a one-to-one connection. between the energy and the temperature. So instead of controlling energy, I will control the temperature of the system. I will heat it up, I will cool it down, and out of this expression, I will obtain what exactly the energy of the system is. The only thing that I need to know is the number of particles, the value of the excited state, the value of the energy at the excited state, and the temperature. You shift the temperature to the right, you shift the temperature to the left, cool it down, heat it up, and you have the energy of the system. Now, it's not the exact energy of the system, right? E, as we told you already, is the average temperature of the system, because in thermodynamics, it's the average, because some of the particles will start to jump up and down, up and down. So this is what we're getting. We don't have time, so we'll continue tomorrow to see what is the heap capacity, dE to dt. It's another couple of lines of algebra, but we'll get there. Okay, see you all tomorrow. Thank you.